So if I go back to the syllabus content to show you, so this is the module that we have completed, or module number 4, which was part of the CAT2 syllabus that we have done. So now we are moving towards module number 5, which supposed to be on diversity techniques. But prior to reaching out to this topic of diversity, ideally the second half, if you see here, this is where diversity comes in. Alright. So prior to going to that part, I think we need to introduce you why or what is the impact of single user or single input, single output or a non-diverse scenario. And before that, we also have to establish that what happens when we consider the bit error rate calculation to be done in a wired scenario to that of a wireless scenario. Because in general, what we understand from our concept for the time being, that for a wireless scenario, definitely the bit error rate will be higher. Alright. Now, in this first part of our discussion, which we are going to do today, we are going to see that how the wired and the wireless scenarios are differing in terms of bit error rate, what are the requirements of it. Then in the second part, we will discuss about what are the effects that causes the wireless scenario to have a detrimental BER process. And last but not the least, which we might be starting on Wednesday, where we are going to start off in the process that after the impact on wireless of different patterns or different parameters, as the BER value is substantially low, then we need to find out a solution to counter that. Now, the process to counter such scenario is basically the diversity, in which MRC, the maximal ratio combining, the equal gain combining on EGC that you are looking at, these all will play an important role, and we will discuss about the diversity order as well. And this portion mostly will be dealt with numericals. Alright. So, in order to establish that part, we need to discuss the first preliminary element. So, in order to do that, let us try to find out the first discussion that we have here. Let me draw this diagram of it here so that we are understanding it. So, if you see, if you observe over here, what is exactly this? We have a symbol which is X, alright, and there is a scenario where something is getting added up as in terms of noise, and we are getting an output of Y. So this is my receive signal, this is my transmitted signal, and this is my noise. Now, what we are trying to discuss over here is a wired scenario. Remember, this is a wire line scenario. That is, there is a dedicated path that exists between the transmitter and the receiver. Alright. So, if that is the scenario that we are talking about, the noise that we are looking at over there will be nothing but an AWJ noise. Okay. Which will be an AWJ noise. So, it is mentioned over here. So, noise at the receiver is mentioned over here. And if you see the expression for it, that Y equals to nothing but X plus N. Alright. And the reason is that you can see that X remains almost undisturbed as such, except that the additive white Gaussian noise is introducing some error to X. Alright. Now, if you carefully observe here that we are not having any disturbance with X, you will soon find that in wireless scenario, when we try to analyze the same, we will come across something of the multi-path scenario that will be coming in front of this X. That is one of the biggest reason why the wireless scenario includes a very poor bit error rate performance. We'll see that one by one. Now, if I consider this particular scenario and also keeping in mind that we have a scenario of BPSK, I guess all of you are aware of BPSK, where 1 bit at a time we are sending the data. In that, X is equals to 1, and this is given by square root minus P. So, this is given by square root minus P as the amplitude of it, and this is given by plus square root P. If it is like that. So, in order to establish a relationship, we are dealing this assumption. We are getting that Y equals to minus square root of P plus N, or it can be equals to plus square root P plus N. So, either 1 has been transmitted or 0 has been transmitted. Right? Now, what will be my error? Error will be if 1 is transmitted and 0 is received, or 0 is transmitted and 1 is received. So, that is basically what the fundamental problems with any of the errors is all about. So, you can understand this is what is mentioned over here, that if the receive symbol is greater than 0 or less than 0, so these are my threshold conditions. So, given the fact that if it is like this, if it is greater than 0, then we will consider it to be 0, that is at the receiver I am saying, and if it is less than 0, then we will consider it to be as 1. But this is the idealistic scenario, where we are sending 0 and we are getting 0, and we are sending 1, we are getting 1. But what happens is that when we consider specifically for bit error rate, if you observe over here, y is greater than equal to 0, although this is the condition, given x is equal to 1. Which means you have sent x equals to 1. So for x equal to 1, y is supposed to be less than 0. But you are getting a greater than 0 condition. So that means there is an error that has happened. That's basically what the bit error is all about. So if that is the case, then we can say, please make a note of this. The condition for bit error rate will only happen. This condition becomes very crucial as we go on with the wireless scenario as well. So the condition of BER suggests that this AWGN noise that we are talking about, this is all with respect to AWGN. Nothing in terms of multipaths in law. That if it is greater than square root of P, I'll still writing it down for a better understanding again. If this condition is satisfied, N is sufficiently greater than equal to P. P here indicates square root of P, square root of P. Okay. If this condition is satisfied, same thing I've written just for understanding. This is called as that there is definitely a chance that BER will happen. So if suppose given a question somewhere you are asked that what is the condition of getting a BER, then the noise value, if it is greater than the signal value, then definitely you will have a amount of bit error rate. Whatever the proportion, that is different, but it will happen. Right? So that's the first thing. Second thing that we are understanding over here is that what is the probability that this condition will happen. So that's why we are making it as probability of error. So what is the probability that N is greater than square root of P? So that is usually computed in this order, where we have a, you can see here it's already mentioned, I'm just ignoring it for the time being, because this is the power density function of the noise, and this is being represented over here. Don't worry about all these calculations and all, it won't be required for you, but it's just what for initiating something. So the probability of, you imagine in this way, that you can see in the right hand side I have written the physical meaning of it. It ideally means what is the probability that the noise is greater than square root P. That is given usually by the integration over minor square root P by integral to that of the PDF function of the noise. Usually that is the rule. And after you substitute everything, just like I did over here, which I am ignoring for the time being, the final expression that we are getting, that is only crucial. So let me write it down here. Please make a note of this equation. So the probability of error or PE is given by Q function square root of SNR. Please make a note of this. I'll rewrite here. PE is equal to Q function of square root SNR, or we can also write it as Q function of square root of P by sigma square. We have seen that both of these are interchangeably used. In some question you might be asked with SNR. In some question it will be signal and noise variance separate. So it means the same. The important point is this is for wired scenario. This is for wired scenario. Alright, so for a P wired, the probability of error for a wired connection, it is nothing but a Q function. Q function, I guess all of you remember, I don't know whether you remember it or not. We have used this in the first module while we were doing the practical link budget calculation. Remember something like Q of threshold was there, gamma minus PL by sigma square. There also we have used the Q function table. So the same Q function comes here. So this is the equation. Now keeping this equation, let us solve a small little question to clarify our doubt. Given that SNR equals to 10 dB, what will be the necessary what is the BER of the system using BPS. So 10 dB usually, whenever this is given, you should convert that to linear scale. So this has been done over here. We have converted to linear scale. Please make a note of it. It is although it is mentioned here, but while doing it, you please make sure. So the linear scale is present over here. So now we substitute over here in this equation q of square root SNR. Now if you substitute over here, you are getting a value of 7.8 into 10 to the power minus 4. Same thing as the written it for our better understanding. So it is 10 to the power minus 4 and 7.8, be irrespective of whatever the value it is. So it's a very small quantity. That's the bottom line. It's a small quantity. So what we can conclude that for a wired scenario, the bit error rate is significantly small when we consider an SNR of 10 dB. Everyone agrees to this? Based on the equation, we have established that. The point is, we have to use a wireless scenario. We can't help it but use it because of the advantage that wireless system provides us. So what our target is that using a wireless scenario, can we attain a almost 10 to the power minus 4 or if not even more smaller value of bit error. But we'll still provide a wireless connectivity between the end user. Because as you know, the advantages of having a wireless scenario, we are the mobility, the other factors that we come across. So we want to get all of those advantages, keeping in mind the PER will be substantially low. But in reality, what happens, that is not the case. So we'll see that after some time. So now this is about the P. Let us conclude on this aspect itself. Now this is a Q function calculation, right? Now this, if you see Q of square root 10, this comes in from the Q table. There is a Q table that we usually look into. But if it is not there, and in almost all the cases you are not going to have it with you, the approximate solution is given by the equation as is given here, which is Q of x. Please make a note of this. Q of x is less than equal to half of e to the power minus half x's square. The same thing is written here. If it is not visible, that's why I have written it down. So basically this indicates that Qx can be approximated. This also has a condition of it. It can be proven as well, but we don't need that. So if there is no table provided, and which in all case you are not going to, because Q function table is a pretty detailed one, and you almost lose out time on that. You just substitute Qx equals to half of e to the power minus x square. Well, x is, it can be square root SNR. It can be g of SNR, you will see sometime later. So whatever it is, the value whatever is there inside. In this case, as we know, this is Q of square root SNR. So you have to substitute square root SNR here. So square root of x square, it means it will become half of e to the power minus SNR by 2. We'll see that. Later we'll see that. The objective is that let's see for the same question, if I use the approximate solution, what happens? So you can see here what we have done in the last part of it. BER is calculated by the approximate solution. The previous one was exact, 7 point something into 10 to the power minus 4 was the exact solution of BER. But this is what we call as the approximate solution. Now you can see over here, when we use the expression over here, half of e to the power minus half of SNR. Why SNR? Because it was square root SNR. So it has gone square. So we get a value which is around approximately 3.91 into 10 to the power minus 4. You see. So you can understand the magnitude of it is different. But 10 to the power minus 4 remains as it is. That is why it is called as an approximate solution. Right? It is close to giving you the correct answer, but it is almost giving you the standard. Because it is like amplitude wise, the most important part here is 10 to the power minus 4 or not. That is more important. The magnitude of it will be very small. So eventually it can be 0.7 and like 7 and 3 will not matter much. But 10 to the power minus 4 and 10 to the power 2 or minus 2 will be a significant change. So approximate solution also gives almost similar data, similar value, right? So this is about the wired part. So to conclude on that, this is all done with respect to BPSK. Remember, we have done all this calculation with respect to BPSK. If I go back a little bit, you can understand here I have started off with a BPSK system. Alright. Now, what will happen if the order of the modulation increases? So, just note down the final expressions for the same. So, this expression is given for QPSK. In the same manner, we can derive it, but we don't need that. Even BPSK derivation is also not required. The final expression is only what we require. So, for the QPSK, it is nothing but twice that of Q square root SN. Please make a note of this. Alright. Q of 2 times primarily because in QPSK, 2 bit at a time we are sending. 2 bit at a time we are sending. So basically the bit error rate also will be twice as that of the previous one. So that is why it is 2Q of square root SNR. And the QAM, if you see, QAM is a very important element because for almost all HD definition, high definition transmission, video transmission, if you say, that can be a mobile data, it can be an HD TV, it can be a gaming, it can be an online, the online lectures for that matter. Everywhere, wherever you think of a high definition transmission, other than QAM modulation, you cannot survive. Okay, so you can see over here this N array QAM indicates what is the order of the QAM. For example, I think almost all of you must have aware of 64 QAM. I think you have all heard about 16 QAM modulation. So in case of OFDM also, there are options where we use 256 QAM also. Where this 256, 64 or 16, whatever call it, this will be a 2 to the power. It should be 2 to the power N QAM. Alright. So this is given by the expression. Please understand carefully. Here, this P by sigma square is given by Ps equal to 2 multiplied with 1 by 2m Q function square root 3p by 4m square minus 1. But interestingly, you can see this P and sigma square also exist over here. And if we significantly take that into account, it will come back to SNR once again. So, in case of BPSK, it was only Q function square root SNR. In BPSK and QPSK also, it is almost the same. But in QAM, what happens? You have the order of modulation coming in on top of the SNR which is there. And this will be a constant term. If you see over here, it will be a constant term. 3 by 4m square minus 1. It will be a constant term which is added on top of SNR. And also there is a factor of 2 into 1 minus n. Okay. So I think these formulas are readily available. Please make a note of these formulas because you might get a question where you have to compare between the probability of error in a wired connection with respect to BPSK and QAM. The same question that we have done, did with the BPSK. Now let us try to see what happens when we use a QAM modulation. So here we have used the QAM, these are different examples, QAM, 16 QAM, 64 QAM. So I have taken 64 QAM as a reference for us. So you can see here I have substituted m equals to 64 and we went on calculating it, and you can understand here 9.5 into 10 to the power minus 2 we are obtaining. Which one is greater? This one or 7.3 or something 10 to the power minus 4. Which one is more BER? This one is definitely one more because it is 10 to the power minus 2 and this is 10 to the power minus 4. Alright. So the logic is that as we go on with higher order modulation, which is required for our case to provide the necessary data rate to the end user, we are actually getting a scenario where even with a wired connection, we will have a significant jump in the bit error rate value. That is what we are establishing. So in wired itself, it is increasing that much. So what will happen with the non-wired scenario or a wireless? That is our intention. Okay. So keeping that in mind, let us try to explain you the diagram for a wireless scenario. So the diagram which was there already, you can see here, we have added a new thing, and that is in terms of another block, as you can see there, and it comes to here. And ideally, this will be little bit changed. The noise now is looking at this. And this will be called as, this is N noise and this is called as H as you can see over there. So that is basically my received signal now. Right. Now, if you see the diagram over here, if I explain it from here as well, transmitted symbol was already there previously. Receive symbol was also there. The ADWJ noise is also there. Okay. But now, since we are dealing with wireless scenario, as you can see from the heading, the H term comes in because of the multi-path symbols. And this has a direct effect on X. And that's why the equation, if you observe here, has changed from y equals to x plus n to y equals to hx plus n. Please make a note of it, not because of questions or anything. This is the fundamental equation for any receiver for wireless scenario. Received data is nothing but a combination of multipath to that of the data plus the noise. Now this noise now becomes an AWJ noise, although it is a Gaussian random variable, and we will consider it most of the cases that this is nothing with the channel. Channel is only this part. That is the main factor. Alright. Now let's see if we calculate in the same manner to find out what is the value of probability of bit error rate. Let's see that. So first things first, let us try to examine the H a little bit. So if you observe here, H is given by some kind of a complex matrix. Here, A into the power J5. What is A? A is nothing but the amplitude of the multipath. Every multipath, suppose there is a transmitter, there is a receiver, and the signal gets deviated from different sources. So after a certain period, the signal will have an amplitude, right? So the multipath has this A as the amplitude. A has the magnitude, and phi, if you observe, this is basically the phase difference that is introduced on the system. Each of the multipath, if there is n number of multipath will have n number of amplitude. It can be higher, it can be lower, it can be anything. And it can be random also. It must be random also. And phi also will keep on changing as far as possible. So if I take this, as we are dealing with SNR part, if you see probability of error that we are calculating, in that received power, if I calculate, earlier it was only P by sigma square. Everyone remembers this P by sigma square? Now, as H needs to be included in the calculation, because that has a role of changing the value of X, you can see the amplitude value or the magnitude of it has been considered over here as H square into P. Alright, why it is average? Because it is basically a complex number. We cannot take that into account for any calculation. So it is taking an average, or you can take an absolute value of it. So that's what it's being done. Now, as it has A as an amplitude, you can see here I have mentioned the magnitude of it will be nothing but A square. When I take H square, it's nothing but A square. So that is being completed over here. So now my SNR value will not be P by sigma square, but it should be A square P by sigma square. Again, I am telling you repeatedly, these all are not required. The final destination is required for you, but this is how we establish it. So you should be knowing at least. Okay. So A square P by sigma square. P by sigma square was already there. A square has just come in. And see further, the final expression that we are looking at is SNR for the fading scenario is nothing but the A square part, which comes in because of the channel, multiplied by the wired line SNR, which is present over here. Okay? So this is very important. This is also a condition of SNR variation with respect to wireless scenario, how it is changing. So it is almost the same except that this coefficient will come in. And the problem with this coefficient is that this part, as you can see over here, eventually this goes to the BER expression as well. SNR was there in BER. In the wire line, what we have done? P of Q function of square root SNR. So the same square root SNR will remain same, but now there will be an A square in between. Okay? A square SNR. Now the problem that I was telling you that why wireless has an issue is that because of this A value. As you can see, A is an amplitude of the fading channel which is entirely random in nature. So we don't have any account whatsoever how it will behave. Whether it will get additive, whether it will deduce or deteriorate the signal, we don't know. So that's why calculating a BER just by the value of magnitude is not a very correct solution. It will not give you the exact data. So that is why in case of when we are doing wireless, normal BER won't suffice the need. And we require something called as average BER. And I want you, all of you, to please make a note of this equation. Last, the box one. How we derived it is given here, but let me ignore that for time being. It is nothing very difficult. Here also we are trying to calculate if what is the probability that the value of the channel condition A square P will come back in the next day itself. If that is less than or equal to the given threshold, okay, given threshold A square P given threshold of N, suppose like this. So we'll see that later. Okay, for the time being, let us not confuse also. Let me remove this for the time being. Alright. So average BER calculated this. Now if you remember, I don't know how many of you can remember it, but still I'll just try to show you one important thing. I guess here. You can see this equation looks familiar. I think in last week only we have done that. Do you remember this formula I told you to keep a note of it while you are calculating between the OFDMA system and a non-OFDMA system? So basically this BER equation, you can see half of 1 minus square root SNR by 2 SNR is what we are dealing with over here as well. Same equation. So this is basically very important because based on this only we will extend most of the discussion in multi-carrier system as well. So in BER for for the normal conventional wired scenario, it was a simple Q function with square root of SNR. But in case of our BER for the wireless scenario, we'll have this complex, a little bit of complex equation for the same one. So let us try to solve questions on this. Let's see how it is impacting our result. So let's see, take an example of SNR of 20 dB. Alright, we take an SNR of 20 dB, take it to the linear scale, so it comes to around 100. We substitute over here. So I can see the expression of this is giving you around 4.92 into 10 to the power minus 3 as the value. Alright, so this is the calculated value. The blue one don't get confused with. What I want you to do is, using the 10 dB, we have done the 10 dB calculation, right, in the BER, in the wired line scenario, that gave us a value 7.82 into 10 to the power minus 4, just a while back. The Q equal to this formula, Q into Q of S square root SNR. This value only gave us the result this. I want you to substitute over there in the equation that we have referred to now 10 dB over here. This was 20 dB, na? I want you to make it at 10 dB, and if you do it, you will get the value of 4.3 in 10 to the power minus 2. So this is average BER at SNR 10 dB. This is BER wired at SNR 10 dB. So if we compare with respect to 10 dB SNR only, a wired scenario is giving you 7.82 minus 10 to the power 4, but a wireless scenario for the same SNR condition, it is providing you a very high value of 4.3. Remember, the 7.82 we received when we are using BPSK. So with BPSK wireless, we are getting a 4.3 into 10 to the power minus 2. Pretty high value of bit error rate. So in this, we have established in this way that how the wired scenario and the wireless scenario differs in terms of the value of BER. And we have also observed that how the BER will have an impact, because we are assuming that wireless scenario and the channel, the multipath channel, will have a role in making this BER to come down. But now with an analytical expression, we are establishing the fact that given a particular SNR, same SNR, a wired line scenario will give us lower value of BER compared to our wireless scenarios. Okay? This is a very good observation, and this is a very good question also, where you compare. Keeping that same mode going, we have another question which I want all of you to please focus a little bit more. The question is something like this, that given that BER of 10 to the power minus 6, I'll just write it down here also. I want to have a system where BER should be 10 to the power minus 6. Okay? I want BER to be 10 to the power minus 6 happens to be a very standard BER value, magnitude of BER. It's very low, very small value. So you can imagine one thing, that in wireless system, we are allowing some amount of error that will creep in. There is no system which will be completely zero. There will be very small value. So as much smaller we can make. That is the main intention. That was the reason why we have used cyclic prefix in OFDMA. We have tried to make sure some redundant bit comes in and holds on that position where the maximum excess delay spread is happening. So all those things are linked up to this. Alright. So we have BER. So the question is, if I want to achieve a BER of 10 to the power minus 6, what should be the SNR in a wireless scenario? It's just the reverse question. So what it's doing, 10 to the power minus 6 in the left hand side, we have to find out what is SNR. We take the necessary approximation. I'm just going a little bit quickly here because it's nothing much. You can do it on your own also. So we do the calculation. We get the linear value over here, 4.99. We take the log of it and we get a 57 dB approximately. Right? Can you do me a favor? Can you at least write the equation for the same for a wired scenario? What will happen? Suppose the question is compare the SNR requirement from a wired and a wireless scenario, keeping that BER should be 10 to the power minus 6. Suppose I give you this question. So wireless I have shown you. In wired, what will be the equation? Wired we know. BER equals to Q square root of SNR. So we want the SNR to happen. So basically what we are looking at, Q inverse BER Q inverse BER square. Alright. So that is what we need. Again, Q inverse is a table from where we can get this value of 10 to the power minus 6. And it is coming as around 4.75 value. Take the square, linear value we are getting, and finally we are getting the dB value over here. So what was the previous value? 57. Here what we are getting? 13.6. So basically the conclusion is that you can see that for a scenario of a conventional, a very simple wired to wireless scenario, we are actually needing around 43 dB of extra power in order to maintain the same performance of 10 to the power minus 6 BER from a wireless to a wired. So again, coming back to what we want to have a wireless scenario for all its advantages. But the advantage is coming little demanding, because to attain a very nice or very high value of low value of BER, we would require a very high value of extra SNR or power requirement, okay, in order to get that particular performance. And now feeding this much of power only for a scenario of this nature, simple scenario, is not very advantageous. So we need different adopting techniques, in which diversity is one of them, which happens to boost this SNR requirement. It will come down, it will make the SNR requirement to come down, and on the other hand, improve the bit error rate to a substantial proportion. That is basically the introduction of diversity and why we require a diversity. We'll come to that maybe next day. But another thing to finish off on this note, that why we require all this scenario, that is, what is the reason behind this extra amount of band or extra amount of SNR? Reason is, as I told you already, that H square part, as H as a multipath is affecting the scenario. This is categorized in wireless scenario as a particular term, and that is called as deep fading. So maybe I'll show you that last one. Okay. Let me just show you that. Now, this is what the last element where we end up our today's discussion is something called as deep fade. As you can see, the reason behind the poor performance of a wireless system. Alright, so this reason behind is basically how those H value, okay, is affecting the overall calculation. So that is being called as the deep fade. And as you can see from the diagram, what exactly is meant by deep fade is given by this diagram. As you can see, there are there's a multi-path scenario. Now there are random values or random drop of signal that is happening at some point. This happens to be the deep fades. Okay. Now this when will happen? We don't know. What are the reason to happen? We don't know, because it depends on the multipath scenario, the foliage, the obstacle through which the signal is penetrating. So it will be different. So as you are moving from one place to another, the geography might change. Accordingly, the multipath will change. So the deep fading scenario might change. But all of this has been taken care of by a single condition. So please make a note of this condition. The condition is given here that if the amplitude, remember A is the amplitude of the multipath component. A is the amplitude of the multipath component. So if the A value, the magnitude of it, if the amplitude of it is less than 1 by square root SNR, it can be proven, as you can see over here, some steps prior to that. If this condition exists, if A is less than 1 by square root SNR, deep fade will occur. You can see deep fade will occur if the multipath channel coefficient drops below 1 by square root SNR. Now that is not in our hand. What will happen, we don't know. And eventually it is so random in nature, which we have established in the previous document, that A is absolutely random. In fact, that is the reason why we were taking average BER. So the randomness is so much that it might happen at times the amplitude will come down to less than 1 by square root SNR. This will prompt into more fading that might happen. More fading relates to more BER which will happen. So we extend our discussion over here. We don't need that. We don't need that. Please make a note of this only. The error, the probability of deep fade. The probability of deep fade that can be given as just the last expression you write over here. Probability of deep fade, PDF. That's why it is one. Not probability density function. This is called probability of deep fade. Probability of deep fade. So probability of deep fade is given by 1 minus e to the power minus 1 by SNR. It's an approximate solution again. Now interesting part is, if you see, if we go on doing with SNR value to be very high, what will happen? If SNR value is very high and you go on taking the approximation as it's mentioned, probability of deep fade is almost equivalent to inversely proportional to SNR. So basically it means the more the SNR, the channel is very good condition, the probability of deep fade, it means it's less. And if the probability of deep fade is more, that means definitely it will affect the channel SNR. Now what is the impact of it? Just last line. Have we established this already? BER is almost proportional to 1 by SNR, because if you observe the equation, half of 1 minus SNR by 2 plus SNR. If you go on rearranging a little bit here and there with an high SNR value, you remember this one, last expression we have mentioned, BER equals to half of minus, what was there, square root SNR by 2 plus, right? So if you take the same condition where SNR is very high and if you rearrange that equation, rearrange this equation, it will boils down to something like BER is proportional to 1 by 2 SNR. Now 1 by SNR is nothing but again PD. So you can see 1 by SNR is equal to this. So which means BER, you can see here what is mentioned, BER is almost proportional to the probability of deep fade. So the important conclusion that we are drawing, that as much as possible, if the channel offers a probability, if the probability of error, probability of deep fade increases for a particular channel, it will definitely increase the chances of probability of bit error. That is for sure. Alright, so that is what we have established over here, that one of the very important relationship actually, that this deep fade, the more the deep fade, the more the BER. Why it is important? Because now when we look at diversity deals with challenging this deep fade. Try to rectify this deep fade. Okay. So from here, we'll start from the next session. All right. Thank you.